So, hello. Today I'm going to present to you RaceMob, crowdsourced data race detection. This is joint work done together with my colleague Christian Zamfir and our advisor George Candea at EPFL. So, this talk is going to be about data races, and what I mean by a data race is a situation that occurs in multi-threaded programs where there are accesses to a shared memory location by multiple threads, where at least one of these accesses is a write, and synchronization operations do not enforce an order among these accesses. So if we look at the spectrum of data races, we can see that there are both data races that developers believe to be harmless and data races that are harmful. We can see that sometimes developers choose to keep data races in their code purposefully for performance reasons. And on the other end of the spectrum, there are cases of data races which had disastrous consequences, causing many losses to both human lives and material losses. But these are the cases where developers are aware of the data races in their program. There are also data races that lurk in programs that the developers are not aware of. To make matters even more complicated, the POSIX standard and the new C++ standards define programs with data races as having erroneous semantics. As we saw in yesterday's talk on studying undefined behavior, the implication of these standards is that compilers can arbitrarily break such programs with undefined behavior. And in this case, they can break programs with data races. In turn, those data races that the developers left in their code for performance reasons, or those that they're not yet aware of, can become harmful. So the key point is that any data race in any given program can become harmful and have bad consequences. So developers need to know where data races reside in their code. So if data races can be potentially disastrous, how do we find them? Well, the answer is we use data race detectors to find them. And broadly speaking, there are two main kinds of data race detectors. Static detectors use abstraction, and therefore they're fast. They analyze all program paths, and therefore they have few false negatives. There is few missed real races. And consequently, they're nearly complete. But their analysis lacks the full path context of actual program execution, and therefore they report many false positives, that is, false race reports. This causes developers to be overwhelmed by the number of race reports to investigate, and either they end up losing a lot of time going through all these reports, or because simply they will lose a lot of time, they don't use such detectors. On the contrary, dynamic detectors detect data races during actual program runs using a single path at a time, and they typically monitor all memory accesses and synchronization operations, and therefore they tend to be slow. But because they monitor actual program paths, they have few false positives. However, their analysis is limited to those paths, and they have many false negatives, that is, they miss the actual races. So even if developers use them, they cannot have enough confidence that they discovered all data races in their program. This, in turn, limits their usability. There are some other kinds of detectors, such as the hybrid ones based on sampling, etc., which still have some of the shortcomings that I mentioned. So bottom line is, existing detectors have important limitations, and therefore they're not widely used in practice. What we would ideally have is the best of two worlds. That is, a race detector that performs full path analysis, that is fast, that has few false negatives like the static detectors, and one that also has few false positives like dynamic data race detectors. So in this talk, we introduce RaceMob, the system that we built to achieve these goals. As I explain various components of RaceMob, I will highlight their contribution to these ideal properties on the top right corner. To narrow down the set of all memory accesses in a program to those that are potentially racing, RaceMob uses static data race detection. This way, RaceMob analyzes the entire program, and therefore it has few false negatives and is nearly complete. Static detection detects potential data races because static detectors lack the necessary context to perform accurate data race detection. RaceMob further reduces the set of potentially racing accesses to likely racing accesses in a later stage that we call dynamic context inference by gathering some more runtime information. Then, RaceMob uses a technique called on-demand validation to conclusively detect real data races in a program and eliminate false positives. Validation is also able to detect if a data race can cause an anomaly such as a crash or a hang. These stages incrementally help RaceMob to lower the overhead of data race detection. However, this is not enough to achieve low overhead for practical race detection. Therefore, RaceMob crowdsources the last two stages by asking users of a program to perform dynamic context inference and on-demand validation for a single race at a time. This allows RaceMob to detect races with low per-user overhead. Another advantage of crowdsourcing the stages is that RaceMob discovers data races that impact real users, and therefore the developers can prioritize their fixing efforts around the data race bugs that affect real users. For instance, in some cases, RaceMob can tag some of the races that are detected as causing a crash or a hang, and this will help the developers again prioritize their efforts. So essentially, RaceMob preserves full path analysis of static data race detection and the full path context of dynamic analysis at user sites. So how does RaceMob fit into today's software usage model that roughly looks like this? Developers develop software and upload this software to a place like the App Store for users to retrieve it. Then users download the program and use it, and occasionally they may report problems in their software which the developer needs to figure out and address. With RaceMob, the flow is similar. Developers again upload the program to the application home. However, then RaceMob instruments the program with instrumentation around potentially racing accesses determined through static detection. The users use the program as they would use the uninstrumented one while performing data race validation. The instrumented programs report detected races back to RaceMob, and RaceMob produces the list of tagged issues. The developers automatically know where in their code data races reside and need not spend time trying to understand and reproduce the problem. Moreover, depending on the consequences of data races, that is, if they cause a crash or a hang, their severity might be updated. In this way, developers have a dynamic view of data races in the program, and therefore they can address more severe races first. So what enabled us to build RaceMob were the following key observations. We view static data race detection as a cheap static analysis that can assist the dynamic analysis and enable it to monitor only the memory accesses that truly have a chance of racing. We can amortize the cost of dynamic detection across many users through crowdsourcing. And finally, by piggybacking on users' normal utilization of applications to validate data races in the meanwhile, RaceMob can detect races that impact those real users. In the rest of this talk, I'm going to first talk about how RaceMob uses an existing static detector for narrowing down the set of all memory accesses to potentially racing ones. Then I will explain our contributions, mainly how RaceMob performs dynamic context inference and on-demand validation in a crowdsourced setting in detail. Finally, I'll present the results that we obtained using RaceMob. But in a nutshell, RaceMob detected 106 real data races in 10 real programs like Apache, SQLite, Memcached with 2.3% average runtime overhead. Now, let's have a closer look at static data race detection and how it is performed in RaceMob. RaceMob can use any static data race detector to statically detect potential data races in a program. We chose Relay, which to our knowledge has the lowest number of false negatives for large programs, therefore it's nearly complete. Static detectors typically walk the control flow graph of a program and they analyze entire program paths at once. They may compute per function summaries, and they compose these summaries in order to scale to large programs. They also monitor the logs that are acquired and released during program execution to perform detection. Here's an example that I will use to describe the later stages of RaceMob as well. This program has 2 threads and 2 different writes to a shared variable x. There are also portions of the program that are protected by a lock, but the accesses to x don't fall within these portions. Therefore, in both cases, the set of locks when the accesses are made is empty. We entirely reuse this phase from existing work, so I'm not going to spend too much time here, but the bottom line is static data race detection marks the 2 accesses to x as potentially racing because the lock sets when the accesses were made were empty. Now that we've seen how RaceMob narrows the set of all memory accesses to those that are potentially racing through static detection, let's have a look at how it further narrows down the set to likely racing accesses through dynamic context inference. Dynamic context inference, or DCI for short, makes the key observation that there are two main reasons for the inaccuracy of static data race detection. First are the errors in alias analysis. Static data race detection may incorrectly think that some accesses alias each other, that is, they may have the same address at runtime, and therefore flag such accesses as data races. Whereas during actual program execution, these accesses may never alias. Second, the static data race detector may be unable to infer multi-threaded program contexts. Static data race detectors typically assume that the entire program context is always multi-threaded, and therefore they do not differentiate between the portions of the program that run concurrently versus the portions of the program that do not run concurrently at runtime. As a consequence of this, static detectors end up having a lot of false positives. This inaccuracy can be addressed using a lightweight analysis that checks at runtime if the accesses involved in a potential data race are made from different threads and whether they alias. If yes, then such races are promoted to the likely racing category. In our evaluation, RaceMob managed to reduce the set of potentially racing accesses to likely racing accesses by 53%. Let's illustrate how dynamic context inference works with the earlier example. In a certain execution of the program, here by a user Alice, thread 1 accesses the variable x, and at this point, RaceMob records that the access is made to the variable at address beef from the thread with ID 1. Then the program continues executing, and thread 2 accesses the variable x, and at this point, RaceMob records that the access is made to the variable at address beef again, but this time from thread with ID 2. Since the accesses of the potential data race alias at runtime, and they can be performed from different threads, DCI will let the accesses proceed to the next phase, that is on-demand data race validation. Now that we've seen how RaceMob narrows the set of potentially racing accesses to likely racing accesses through dynamic context inference, let's have a look at how it detects actual data races using on-demand validation. The purpose of on-demand validation is to run a data race detection algorithm to conclusively determine if the likely racing access is actually race or not. On-demand data race validation uses a dynamic happens before based data race detection algorithm. That is, it tracks synchronization operations, and it has few false positives. A happens before relationship is established through synchronization operations such as locks and unlocks, such as in this example. And here we say that the events that happen before the unlock in thread 1 happen before the events that happen after the lock in thread 2. Therefore, the write to X in thread 1 happens before the write to X in thread 2 in this example. But this is a standard data race detection technique. And our contribution comes from our algorithm that tracks the minimal number of runtime events necessary for accurate happens before detection, which therefore reduces the runtime overhead. On-demand validation works by only tracking the memory accesses of the potential data race, as well as synchronization between these accesses. But it will start tracking synchronization operations whenever the first racing access is made, and it will stop either when the second access is made or even before, if a happens before relationship is established between the first thread that made the access and all the other threads. This aggressive starting and stopping of the tracking of synchronization operations contributes to the low overhead of RaceMob, as we will shortly see. Finally, on-demand data race validation will steer the program execution by carefully preempting threads at the right time to expose data races. To better understand how on-demand data race detection works, let's continue our example where DCI previously identified that the accesses to X can happen in different threads and that they can alias. Let's imagine that a user Alice executes the program as follows. Thread 1 goes ahead and accesses the shared variable X, at which point RaceMob starts tracking synchronization operations. Then it grabs the lock, continues executing, releases the lock, and at this point the execution switches to thread 2, which grabs the lock. Now, if these are the only two threads in the program, RaceMob stops tracking synchronization operations because the happens before edge between the thread 1 and thread 2 ensures that any following access to X in thread 2 won't be racing with the access to X in thread 1. This program continues executing, and RaceMob tags this execution as not having a race because of the happens before edge. Note that the tag is for this execution only and not for the data race itself. At this point, RaceMob knows that for Alice, the access X equals 1 executed before access X equals 2. So RaceMob's objective is to ensure that Bob witnesses an execution with an alternate order of the accesses witnessed by Alice. This is why, if Bob executes the same program, and the program attempts to first perform the access to X in thread 1, just as in Alice's execution, RaceMob will preempt thread 1 and let thread 2 run until it accesses the variable X. Only then RaceMob will let thread 1 to be scheduled and access the variable X and execute the program until its end. Now in this case, since there is no intervening synchronization between the accesses to X, RaceMob will tag this execution as having a data race. Finally, RaceMob gathers the results, and since one user saw an execution with a data race, RaceMob tags the potential data race as having an actual data race. So users report these validation results to RaceMob, and RaceMob processes various reports that arrive from the users to tag each potential data race. If any user encounters a data race, then RaceMob simply tags this as a data race. And if any user encounters a crash that's associated with a data race, then the data race is tagged as causing a crash, and similarly for a hang. If all users determine that the accesses for a potential data race are actually not racing because they happen to be properly synchronized, then RaceMob tags this as a no race. And if dynamic context inference phases determine that the accesses do not alias and cannot be performed from multi-threaded program contexts, RaceMob will tag the races with according tags. And finally, if no user encounters a particular data race, it is tagged as a not seen data race. So in the beginning of the talk, I told you that this is a dynamically updated list, and the developer can choose to prioritize some races versus the others. In this case, you can imagine that the developer will want to first fix data races that causes crashes and hangs, as opposed to fixing the other ones. We just saw how RaceMob performs on-demand validation. Let me just remind you that RaceMob performs dynamic context inference and on-demand validation in a crowdsourced setting with a single user performing dynamic context inference and on-demand validation for a single data race at a time. Now that we've seen how RaceMob works, I will talk about some of the evaluation results that we obtained using RaceMob. We evaluated RaceMob using 10 systems like the Apache web server, SQLite embedded database, Memcached in-memory object cache. Our results are mainly obtained using a simulated environment, and we performed a detailed evaluation of RaceMob to see whether it's practical, and we answered the following questions. We first looked at the effectiveness of data race detection. Then we examined the contribution of various techniques that we used within RaceMob to lowering the overhead of data race detection. Following that, we examined in detail the sources of overhead in RaceMob. We also compared RaceMob to other data race detectors and concurrency testing tools. Finally, we performed the scalability analysis of RaceMob. Today, I only have the time to talk about the first 3 items, and therefore I encourage you to look at our paper to see the rest of the evaluation. Let's first have a look at the detection results. On the x-axis, we have the various tags that RaceMob assigned to statically detected data races, and on the y-axis, we will see the total number for each tag. RaceMob's static data race detection phase detected a total of 841 potential data races across all the 10 systems. RaceMob's static detection, out of these 841 races, 106 are true data races, which amount to 13% of all the detected potential races. 3 of these races caused a crash, and 3 of them caused a hang. RaceMob identified that 621 potential races are not actual races. that is either because of alias analysis or multi-threaded context inference errors in static data race detection, or simply because the static data race detector could not identify happens before relationships that were present in the program and were introducing an order, a proper order among the accesses. Finally, 10% of the potential data races, which amount to 84 data races, were not seen during the executions that RaceMob monitored. In conclusion, RaceMob detected and confirmed a total of 106 true data races. We then looked at how various techniques that we used within RaceMob help lower the overhead of data race detection. For this, we took two programs, Ocean, which is CPU bound, and PBZip2, which is IO bound. We see these systems on the x-axis, and the y-axis represents the ratio between the detection time and the actual non-instrumented execution time. First, we show the overhead of using pure dynamic data race detection with Thread Sanitizer, which is a state-of-the-art tool from Google. We show this as the full overhead for both systems in the beginning. This is because dynamic detection monitors all the memory accesses and synchronization operations in the program. We then first performed static data race detection prior to performing dynamic data race detection. This lowered the overhead to 26.1x from 30x in the case of Ocean, and to 6.3x in the case of PBZip2. This improvement is due to static data race detection, which narrows down the set of memory accesses to monitor. Ocean performs intense synchronization, therefore static detection does not help lower the overhead of race detection as much as it does for PBZip, which is not synchronization intensive. Then, enabling DCI and on-demand validation lowered the overhead to 3.6x of the initial overhead in the case of Ocean, and to 5.4x in the case of PBZip. This aggressive start and stop of tracking synchronization operations paid off well in the case of Ocean, which is synchronization intensive. Finally, we crowdsourced the entire operation of RaceMob, in this case to a couple hundred users, to further distribute the overhead, which would otherwise be expected by a single user. This reduced the overhead to 1.01x in the case of Ocean and 1.03x in the case of PBZip2. We can see that there is a high variance in the contribution of each technique, and we conclude that neither technique is dominant in reducing the overhead on its own, but the real benefit comes from their combination. Said differently, removing any one of the techniques will impact the overhead significantly. Finally, we looked closer at the average runtime overhead per user for RaceMob to see whether it's usable in practice. On the x-axis, there are 10 different programs that we evaluated RaceMob on, and on the y-axis, we see the percentage overhead of RaceMob over native execution. We split the overhead in two components. The first one is solely due to instrumentation code that's present in the programs, and the second component is due to dynamic validation. The instrumentation component, which is the blue bar on the graph, typically accounts for below 1% of the overhead for the programs in our evaluation, with the exception of FMM, for which it's around 2.5% because of tight loops and memory intensiveness. The maximum overhead per user is 5%, and the average overhead per user is 2.3%, which in our opinion is negligible. In conclusion, let me recap the main ideas behind RaceMob, our data race detector that first statically detects data races, then offloads the validation tasks to the crowd to perform dynamic context inference and on-demand validation. RaceMob uses static data race detection as a static analysis that assists the ensuing dynamic analysis and enables it to monitor fewer memory accesses and the memory accesses that truly have a chance of racing. RaceMob also reduces the cost of dynamic detection by spreading it across the crowd. Finally, by piggybacking on users' normal utilization of applications to validate races in the meanwhile, RaceMob can detect races that impact those users. RaceMob detected 106 real data races in 10 real programs with an average overhead of 2.3% per user. This brings me to the end of my talk, and I'd be happy to take your questions.
Yeah, Ken Berman. Forgive me if this is a very naive question, because it may be. I don't follow this area as much as I should. But I'm curious about threads that are created in response to some form of I/O event. For example, a GUI that spins off a thread each time you click a button. It strikes me it's very hard to predict the number of such threads that might be running dynamically. And so I'm curious to know how tools of this kind deal with that form of additional uncertainty of when threads are created. And I imagine there are other such cases,
So
too.
we intercept all thread creations and dynamically maintain a count of threads that are available in the system at any given moment. So therefore, we will only stop if it happens before a relationship between the thread that made the first access and all those other dynamic threads are established. So this is dynamically maintained property, so we will handle such cases.
But you can't statically predict.
Yes, we cannot statically do that, yeah.
Hi, I'm John Osterhout from Stanford. Using your users to find bugs in software is a long-standing tradition of commercial software companies. But it seems like you take this to a new level in that it seems like now you're going to have software out there that's actively trying to make the software break for every one of your users. Would that be an impediment to this being adopted by commercial companies? Or would that be considered a plus?
I guess so. That's a really good question. That's a rather philosophical question. What we believe is that it might be beneficial to sacrifice some users for the better of a large population. So if you think of it, such a scheme is going to allow you to make your software better in a much quicker way. But of course, this option of tweaking schedules and exposing potential bugs is adjustable. So we need not have that. If any one company has a concern of doing that, this is just an adjustable option. It can just be turned off. But we believe that it should be there, and software should get better much faster.
Hi, Rich Draves, Microsoft. I'm curious if you looked at all at the kinds of applications that are found in application stores, not so much those scientific or system codes. I mean, do those typical applications in application stores, do they have many data races in them? Is there much to find?
So we did not look at those because the static data race detector that we used off the shelf was able to analyze only a subset of C programs. So we can definitely build a static detector that can analyze a more general class of programs and make such an analysis. But we haven't looked at that.
Okay, so there is a question from Google Moderator. Most of the data races in popular programs are not vulnerable due to compiler optimizations, since these variables are marked volatile. What fraction of the races you detected in popular programs were actually harmful? Okay,
so out of the 106 data races that we detected, 3 of them caused the hang and 3 of them caused the crash. So 6 of them were actually harmful. But the thing is, so most of these data races that we detected are actually not on variables that are marked volatile. And the implication of this is that with the new standards that we have at our disposal, the compiler implementers are increasingly more liberal in implementing optimizations that will actually take those seemingly benign races and turn them into harmful data races. So this will be more likely as we progress into the future.
Hi, Jed Liu, Cornell University. I just wanted to comment that it seems like you could take the schedule steering and flip it on its head. And basically, once you find a race that is benign, you can steer all your users to that schedule.
That's a very good idea. I agree.
Ben Blum from CMU. I have a clarification before my actual question. When you talk about 5% overhead, 2% overhead, is that the average overhead incurred across all users?
So the 2.3% is average overhead incurred over all users. And the distribution is pretty uniform. And the maximum is across all users 5%. So there's no great outliers.
Okay, you mean there are no great outliers across the different programs that you're testing?
Yeah.
So my question is, in the paper about schedule steering, you discuss using timeouts on the barriers and having the users rerun. For each individual user, according to these timeouts, might the user incur very little overhead sometimes and a lot of overhead sometimes? So is that a high variance thing or is it a low variance thing?
So for the programs in our evaluation, we set these timeouts manually, and you can envision that developers actually go ahead and set these timeouts manually as well, depending on their application behavior. So the timeout is going to increase overhead in the cases where you stall one thread if other threads are not able to make any progress. And by just stalling that thread, if you stall the entire application, you're going to incur a runtime overhead. But this doesn't happen all the time. So if you can stall one thread and you can let some other threads run, and by stalling that other thread, you can enforce the order that you want without even incurring any runtime overhead.
Thank you.